We saw in the last video that we desperately need a way to find the projection of u onto v and its scalar quickly and easily without having to do it just by eyeballing on a grid, because even simple ones we were not able to find just by looking at the drawings on the grid. Alright, so when you have your u vector here and it has a magnitude u, right? And then you have your v vector down here, there's a shadow that's cast that is that projection. And it's orthogonal to the v vector. So that's the projection right there. So the length of that projection would be the scalar. So I'm going to call it x. So that would be the length of this. So it would be the length of the projection of u onto v. So I'm going to call it x right here. Okay, well, let's think about some things that I know here. I know that I'm forming an angle when I create this. So there's an angle theta that's right here between the u vector and the v vector. All right, okay, well, what do I know about that? I know that the cosine of that, because there's a right triangle right here, the cosine would be x divided by the hypotenuse, but the hypotenuse is the magnitude of v. So let me write that. So the cosine of theta would be equal to x, which is the scalar piece, divided by the hypotenuse, which is the magnitude of the u vector. Gotta love that trigonometry. All right, so this is the scalar of u onto v. Right, it's the length of that projection. That's what the scalar is. Okay, but that means that x is multiplying both sides by the magnitude of u. It's u times the cosine of theta. All right, well, that's all well and good, but we don't always have that. Well, and even if we do, there's something else going on. So let me just multiply, because I can, by the magnitude over the magnitude. Right? I can do that because that's really just 1. And you can always multiply by 1 because it's not really changing the problem. So let me rewrite this. This would be u, the magnitude of u, times the magnitude of v. And now, hopefully, you're starting to see why that is in this section. Little bells should be going off in your head. Because uv cosine of theta is the dot product. Yes? And then, of course, it's all divided by the magnitude of v. So what we've just learned is that the scalar of u onto v, which is x, is equal to the dot product u dot product with v and divided by the magnitude of v. Because that entire numerator is the definition of the dot product. Right here. Oh, but it's down here, huh? That's where it comes from. So we just proved that this little formula works. So this formula right here for the scalar is in fact this formula here for the scalar. They are one and the same. My paper got squishy there. Lovely. Okay, what about the direction of the projection of u into v? So that would be the unit vector in the v direction. I better write that. So that's the unit vector in the v direction, right? Because that'll get us our direction, and that would be v divided by the magnitude of v. Okay, that's nice. And now we're going to use that because that's going to get us direction right here. So we know the length. The length would be the scalar. So if I have the length, that's this part right here. Right? So length is the scale of u onto v. times the direction, but we just proved what that was. That is the v vector divided by the magnitude of the v vector. Interesting. But the scalar we just said right here is equal to u dot v. So this is u dot product with v divided by the magnitude of v, all multiplied by v over the magnitude of v. Okay, well, v is parallel to v, therefore the dot product, this is just a little note over here. So note, v, the v vector is parallel to itself. Therefore, v dot v, right? V dot v would be equal to the magnitude of v times the magnitude of v. Sorry, that got a little strange. It has to do with the definition of dot product for parallel vectors back several pages. So this is the case, and that's going to help us with our denominator, right? So we're going to use that for that denominator. So the denominator is going to be v dot product with v. So I have u dot product with v, and now I have v dot product with v, right? U dot product with v, v dot product with v, all multiplied by v. Which is interesting because this is going to be a number, right? So a scalar will be a number. Because it's a scalar, it will be a single number. It'll be the length of the projection of u onto v. That's when you find the scalar, you're finding a single number, a scalar, right? Over here, not so much. That's not a scalar. That is a new vector. You can tell because it's multiplied by one vector. So the dot product on the top becomes, well, one dot product, right? And the dot product on the bottom becomes another one, right? And dot products are actually whole numbers. So this part right here is a scalar. This part right here is a scalar, right? Each of these pieces. Those are scalars, but then it's multiplied by this other vector v. So you're basically taking a number times a vector v. Here, let me highlight this. Right? That's where that's coming from. So this piece right here is equal to this piece right here. But that's a new vector in the v direction. So this is a new vector in the v direction because it's multiplied by v right there. So this dot product gets you a number, a scalar. This dot product gets you a number, a scalar. And then you multiply it by this vector v, which will get you a new vector in the v direction. All right, so let's practice, shall we? No drawing required, so we won't put a grid, we won't try to eyeball this, we're just going to do this. So they want to find the scalar and the projector. So let's see here. I'm just going to kind of divide my paper up into two, that way we don't get it all mixed up. Sure. Okay, so the scalar v onto u onto v is equal to, and what we do is we take the dot products. So you can see right here, this is, let's see, 5, 0, 15. That's u. And v is 0, 4, negative 2. It just occurred to me I should probably color code this. So this is 0, 4, negative 2. That's v. I'm going to erase u and make it pink. Oh, sorry, my dog is barking in the background. Okay, so I'm going to take u dot v, so u dot product with v, and I'm going to divide it by the magnitude of v. Right, that's the formula. So you take u dot v, you divide by the magnitude of v. So I'm going to divide by the magnitude of v. Okay, so that would be, let's see, 5, 0, 15, dot product with, let's see, 0, 4, negative 2, all divided by the magnitude of that. So that'd be the square root of 0 squared plus 4 squared plus 2 squared. Of course, since everything's squared, you don't have to worry about the negatives. It's easier if you just make everything positive. Okay, dot product. Remember, the quick way is to just multiply. So 5 times 0 is 0, 0 times 4 is 0, and 15 times negative 2 is negative 30. So that gets us negative 30 divided by the square root of 16 plus 4, so square root of 20. 4 goes into that, so that's negative 30, 2 square root of 10, which would be negative 15 over the square root of 10. It's a scalar. It's a number. Right? Okay, now what about this one, the projection part? So the projection of u onto v is equal to, and it's a little more complicated, so we've got to do, let's think, u dot v, oh, oops, v, there we go, and then v dot v. So u dot v, we have v dot v down here, and then it's going to all be multiplied. So dot product here, and the whole thing is multiplied by the v vector. All right, so let's think. I need u dot v, which I've actually already seen because I did it over here, but I'll just write it out for us for our notes, so that way we have a sense of how to do this. And we're going to dot product that with 0, 4, negative 2. And then the whole thing is going to get multiplied by 0, 4, negative 2. So down here I'm going to have 0, 4, negative 2, dot product with 0, 4, negative 2, and the whole thing is multiplied by 0, 4, negative 2. So inside the parentheses I'm going to get a scalar. I'm going to get, let's think, negative 30 for the top, because we already did this. 5 times 0, 0. 0 times 4 is 0. 15 times negative 2 is negative 30. 0, 4 times 4 is 16. Negative 2 times negative 2 is 4. 16 plus 4 makes 20. So it's negative 3 halves multiplied by 0, 4, negative 2, which would be, well, let's think. We can just cancel out the zeros, right? So 2 goes into 4 twice. 2 times 3 is 6, so it's negative 6. 2 goes into 2, negative 1. Negative 1 times negative 3 is 3. And there you have it. This, for the first part, was a scalar. This is a new vector. A projection is a new vector. The scalar is the length of that projection, so that'll be a number.